You ever just stop and think about what's actually happening when you write code? We type these abstract ideas into an editor, and somehow they just spring to life inside a machine. It's pretty amazing. So today, let's pull back the curtain on one small but totally fundamental part of that whole process.
I mean, think about it. We create variables all the time, right? But where do they physically live? What's the system that gives them a home inside the computer's memory so our program can actually find them again later?
You see a simple line of code like this one. Looks so straightforward, doesn't it? We're just making a variable called score and giving it a value. But behind the scenes, there's this really sophisticated system at work, and its whole job is to decide exactly where in the computer's vast memory this little piece of data is going to live. And trust me, it is not random. It's a very carefully organized process.
Now you might be thinking, okay, but why should I care? As long as it works, right? And that's a fair question. But understanding this invisible system, this sort of memory map, it's one of those things that really separates a good programmer from a great one.
So why does it matter? Well, knowing this stuff helps you hunt down those super weird, tricky bugs, the kind that only happen after a function runs 1,000 times. It lets you write smarter, more efficient code because you actually get the real cost of what you're asking the computer to do. It's pretty much the blueprint for how your program even exists in the first place. So today, let's explore the two main ways the system gives your variables an address.
All right, let's start with the first and, honestly, the simplest method, static allocation. The name kind of gives it away. This is all about creating a fixed, unchanging home for our data.
So with static allocation, this special program called a compiler does all the heavy lifting ahead of time. Before your program even starts running, the compiler just scans your code, figures out exactly how much space certain data needs, and assigns it a permanent address. And that address, it will not change for the entire time your program is running.
And the perfect way to think about this is like a P.O. box. Imagine your program needs to rent a P.O. box for something like a global variable, a piece of data that needs to be available everywhere. Well, that box gets a specific number, its address, and it belongs to that variable for the entire life of the program. It's simple, it's reliable, and it's permanent.
And this is basically what it looks like under the hood. Now, don't worry about the syntax here. This line of code is from a classic compiler textbook, and it's just a direct instruction to the machine. It's saying, hey, store this piece of information at this specific pre-calculated static spot. It's not figuring it out on the fly. The P.O. box number is already known before we even start.
Okay, so that's the permanent setup. But what about all the temporary stuff? That brings us to the other main method, stack allocation. If static is all about permanence, the stack is all about creating temporary, flexible workspaces for tasks that are happening right now.
Most of your variables, especially the local ones you create inside functions, they live on what's called the stack. So when you call a function, it gets a temporary chunk of memory to do its work, and when the function is done, it just gives that memory right back. It's this really elegant last-in, first-out system.
The cafeteria tray analogy is just perfect for this. Imagine when a new function gets called, it's like someone grabbing a clean tray from the top of the stack. They use it for their meal or, their calculations, and when they're finished, they put it right back on top for the next person or the next function to use.
And yep, you guessed it, this is that stack. If you have a function that just keeps calling itself over and over again, a runaway recursion, it's like grabbing tray after tray after tray without ever putting in any of them back. And eventually what happens? You run out of trays, the stack runs out of space, and your program crashes. That's a stack overflow. And here's the instruction that makes it all happen. The computer uses this little bookmark. It's called the stack pointer, or SP, just to keep track of the top of our stack of trays. This command here, add_sp, is literally the machine making room for a new tray. It's pushing that bookmark up to reserve a new workspace for the function that's about to run. So let's just put them side by side for a second. Static is permanent. It's like that P.O. box, and it's used for things that need to stick around, like global variables. The stack, on the other hand, is temporary. It's like a cafeteria tray, used for the quick, dynamic work of local variables inside functions. They're just two different tools for two very different jobs.
Okay, so let's see how these ideas actually work together in the real world. We're going to look at one of the most common things a program does, calling a function. And this whole process, it relies almost entirely on the stack.
It's really like a little four-step dance. First, the caller makes room on the stack for a new tray. That's our add_sp instruction. Second, it leaves a little note on the old tray saying, hey, come back here when you're done. Third, it jumps over to the new function's code. And finally, when that function is finished, it just looks at the note and jumps right back.
So let's peek behind the curtain at the actual machine instructions that make a couple of these crucial steps happen. They might look a little cryptic at first, but the idea behind them, as we'll see, is actually really simple.
This instruction right here is our step 2. The ST just means store. It's telling the computer take the return address, let's say it's address 152, and store it at the very top of the stack, which is what our stack pointer, SP, is pointing to. That's the come back here note.
And this is step 4, the return trip. Just means branch, which is really just another word for jump. This tells the computer, hey, look at the very top of the stack, find that address we stored there, and just jump to it. The function has read the note and is now giving control right back where it started. Simple as that.
You know, when you step back from all the low-level details of stack pointers and memory addresses, the bigger picture is what's truly fascinating.
What we've been looking at today, it isn't magic. It's a beautiful, logical, and really well-ordered system. It's the machinery that takes our abstract ideas about variables and functions and gives them a real, actual home inside the machine, which is what allows our code to come to life. And this is just one small piece of that puzzle. It makes you wonder, doesn't it? What other invisible, elegant systems are just humming away beneath the surface, quietly making our entire digital world possible? It's something to think about.